Hello and welcome to today's video. In this video we are going to introduce one of the central notions of calculus, and that is the notion of continuity. So this section is titled Continuity, and we'll again start with an example. Now you might recall the example of the disinfectant wholesaler who had a rather strange pricing function. If you don't, that doesn't matter. I'll remind you in just a second. So recall the disinfectant wholesaler. With price function f. And remember, the price function looked like this. So you will hopefully remember the minimum sales was 500, the maximum sales was 2000. So the domain of that function is the interval from 500 to 2000. The price is always non-negative, so the codomain is r greater or equal to 0. And the price worked as follows. If you order between 500 and 1000 liters of disinfectant, you pay 3 euros per liter. So that's the first branch here. If you order more than 1000, up to the maximum order of 2000 liters, you pay a fixed amount of 2500 euros for the first 1000 liters, and then 2 euros for each additional liter. So that is this term here. And that, of course, can be simplified to 500 plus 2x, where x is the total order quantity. Now, the graph of that function looks like this here. You have the order quantity here on this axis, the total price of your order on this axis. And as you can see, between 500 and 1000 liters, we follow this line here. And then the price jumps down. And that seems somewhat unnatural. You order more, but you pay less. So, of course, the wholesaler would like to avoid something like this. So let's say the wholesaler would still like to keep this part of the function fixed. He or she would still like to keep this final point here fixed. But this here, this jump, should be avoided. So what can we do? Well, let's copy that graph and try to modify that accordingly. So again, the wholesaler would like to avoid the jump in the total price. And proposes the following change. And now the change graphically looks like this. We take this old function here, and let's remove this part here. We keep these old points intact. And to avoid the jump, what we do is we just connect these 2 points directly, avoiding the jump. So what do we get here? Well, the new pricing function, f of x, is then the same as it was before in the first branch. So we still have 3x for x in the interval from 500 to 1000. We did not change anything there. And now in the new part, what we get here is, well, let's see. Here we go from 1000 to 2000. So the difference here is 1000. And here we go from 3000 to 4500. So the difference here is 1500. And that means the function value grows at a rate of 1.5 the change in the order quantity. So what we have is a 1.5x plus, well, what's the base price? If we start at x equals 1000, then 1.5x is 1500, and we need a starting price here of 3000. So that means we have to add 1500 to that term to get the actual function in that branch. So that holds for x in 1000 to 2000. And to make that definition unique, to make the branch unique, we still have to exclude 1000 from this branch here, although the values will be the same. It doesn't really matter. Now, what we obtain is a new function where the limit of f towards that x value here actually exists and is this point here. Remember, in the old version, we had a limit from the left and a limit from the right that existed, but they disagree. So there is no limit of the function for this x value here. And now this limit does exist. So that's the change that we made. So that means now the limit of f of x for x tends to 1000 exists. And furthermore, it is equal to 3000, which is also the function value at 1000. So the limit doesn't only exist, but it also is equal to the function value. Another possibility would be for the limit to exist, but for example, to jump somewhere. And again, that would not make for a very natural price function, so we want to avoid things like that. And functions that avoid these unnatural jumps, so to say, those are called continuous functions. For a precise definition, we use this property that we just observed here. What we want for a continuous function is that the limit at all points exists and is equal to the actual function value. The limit is basically the function value that is suggested by the neighborhood of a certain point. So the function value that the function should take on that we would expect from observing the neighborhood, and then the function value actually should adhere to these observations. That's what continuity is in broad terms. For a precise definition, let's write that one down. Again, we want an interval, and we want a function defined on an interval so that we can define meaningful neighborhoods of points. One can extend that to different scenarios where maybe an interval is not necessary anymore, but we won't bother with these extensions because it will not be necessary in the scenarios that we'll be looking at. So let I be a subset of R, and let that be an interval. And let f be a function defined on I. So I is the domain, R is the codomain. Then let's first define what we mean by continuity at a certain point. F is called continuous at a point x star in I if the limit of f of x as x tends to x star exists and is equal to the value of the function. So that's continuity. The value doesn't jump away from what the neighborhood suggests. Second observation, of course, we can also define left or right continuity at a certain point. And that would mean the function value is equal to what the limit from the left or the limit from the right suggests. So a function f is called left or right continuous at a point x star in the interval if either the limit of f of x as x tends to x star from below is equal to the actual function value. So that is left continuous, or the limit of f of x as x tends to x star from above is equal to the actual function value. That is right continuous. So if you look at the example here above, the limit for that x value here from the left is exactly this point here. So that function is left continuous. From the right, the limit is this point here, but the function value is actually this point here. So those do not agree, and that means the function is not right continuous. So that's an example for a left continuous function, but not right continuous. Yeah, whereas this function here, the limit from the left is this point, the limit from the right is this point, the limit itself is this point, and the function value is also this point. So that function is both left continuous and right continuous and continuous. And of course, continuity would imply left and right continuity and vice versa. If a function is left and right continuous at a certain point, then it also is continuous. Last part of the definition, a function is called continuous on an interval on the domain if it is continuous at every point of that domain. And of course, the same is true for left and right continuity. So f is called continuous or left and or right continuous and one might add on I, or if you don't add that, then we always mean on its domain if f is continuous or left, right continuous for every point x star in I. So this is the rather simple definition of continuity. The limit for every point exists and it agrees with the function value. Now, if a function is continuous or not is often easily observed by decomposing it and then applying a theorem that we would expect that says that basically composition of continuous functions are again continuous. And that's the theorem that we're going to state right now. And of course that stems from the similar theorem for limits that we've discussed before. So if we have functions that are continuous, two functions f and g defined on an interval I, let those be continuous functions on an interval I subset of the real numbers, then the following is true. The sum of two continuous functions, the difference of two continuous functions, and also the product of two continuous functions are again continuous on the whole interval. Part 2. The quotient of these two functions, so f divided by g, may not be continuous everywhere, but it is continuous everywhere where it's defined. And that is all values of x where g of x is not 0. So this is continuous on I, with the exception of all x in I, where g of x equals 0. Third, of course, you can always multiply a function by some constant and it still will be continuous. More precisely, that's a special case of this rule here, because a constant function is continuous. So if one of those functions is constant, then this case is covered, but still that's listed separately for the sake of completeness. So for a constant alpha in R, the function alpha times f is again continuous. And finally, if we combine two continuous functions by concatenation, then the result is also continuous. So more precisely, let's say we have a continuous function, we call it h, defined on some interval j with a codomain I. So this is a continuous function on an interval j subset of R. The function f after h. So that means we use h first, h maps from j to I, and then we apply f to the result. So the codomain is R. This is again a continuous function, and it's continuous, of course, on its domain on j. So concatenation of continuous functions also yields a continuous function. Quick remark here, as you can see, the sum of two continuous functions is again continuous, and the product of a continuous function and a constant is continuous. So basically what that means is that the space of continuous functions forms a vector space. And that's the remark here. So for an interval I subset of R, the space denoted by, and the notation here is C0 of I, and that means all functions with a domain I that map to R such that f is continuous on I. So this is the space of all continuous functions with domain I. That space is a vector space. And now let's round this off with a few examples of continuous functions. Before we have a look at some more interesting, more intriguing applications. First example, a very simple one. Let's say we have a function that maps from R to R, and that is defined as f of x equals gamma, gamma in R, a constant. So very simple function, it just assumes a constant value on the whole domain. Then this function is of course continuous. Simply because the limit of f of x for any x star, right, that will always be, well, the function is equal to gamma everywhere, so that's the same as the limit of gamma as x tends to x star, and that of course is gamma. And that incidentally is the function value. And that's true for any x star in R. So that function surely is a continuous function. So a constant function is continuous. Part B, as the next complicated building block, so to say, the function that maps x to itself, the identity. So again, we'll take R as the domain, R as a codomain, and we define f of x as simply x. Again, that function is continuous on R. And of course, that's also easily seen if we compute the limit of f of x as x tends to some x star, then, well, f of x is always equal to x. So that's the same as the limit of x as x tends to x star, and of course that is simply x star, which is equal to the function value of f at x star. So this is a continuous function, and that is true for all x star in the domain. And now using these two simple building blocks, we can immediately infer that all polynomials are continuous on R, because a polynomial is just a sum of monomials, and a monomial is either a constant or a product of functions of that kind here. And we sum up these products of these functions, and all of these are continuous. So of course, by the theorem that we've just seen, all polynomials on R are continuous functions. And almost with the same argument, if we have two polynomials and we look at their quotient, then of course that is also continuous for all points that are not roots of the denominator. We have to exclude those now. So all rational functions are continuous almost everywhere. So those functions are functions of the form p over q, are continuous, where p and q are polynomials. And those are continuous on R, with the exception of all x in R where the denominator is 0. We have to exclude those points, of course. Okay, finally, I'd like to introduce two functions that are not continuous as a counterexample, so to say. The first one is the floor function. The floor function, we might meet that more often in the future, is usually denoted by this symbol here, right? So this symbol, and just write that around the argument. That is a function from R to R. And it's defined as, well, the floor function of an argument x is the maximum integer that is less or equal to x. So the maximum of all said in z such that this z is less or equal to x. So what we do in effect is we round x down to the nearest integer. So for example, if we have something like 1.7 and we take the floor function of 1.7, we round that down to the nearest integer, that's 1. If we take the floor function of 5, we round that down to the nearest integer, that's 5, right? So rounding down doesn't change that. If we round down minus 1.7, for example, again, we round down to the nearest integer, so that's minus 2 this time, not minus 1, but minus 2, because we always round down, right? It's always the same direction. And this floor function is, of course, continuous on every open interval between two integers because it's constant there. Right, so if you take any integer and an integer z and then z plus 1 and take this interval, it's constant on that, with the exception of the boundary points. So the first thing that we can note is the floor function is continuous on every interval of the form z plus 1 for any integer z because it's constant on that interval. It only jumps at the boundary points, or one of those boundary points. Furthermore, if we round down, well, z, it's going to be continuous here. So if we round that down, it's going to be right continuous, but not left continuous. I'll show you the graph in a second to make this a little clearer, but let me write that down first. So furthermore, the floor function is right continuous on all of R, but not continuous for any integer because it jumps at those points. It's not continuous for x star in the integers set. Yeah, simply because the limit of x as x approaches an integer set from above is, well, what we do is we round down, right? So we always have x as greater or equal to set. We round down, so we always get set itself. And that, of course, is the function value at that point. Rounding down an integer yields that integer. So the limit from above is equal to the function value. But what if we look at the limit from below? Well, now the x values are smaller, strictly smaller than set. And we round down to the nearest integer. It means we go to set minus 1. And that, of course, is not equal to the function value now, right? So the function value will be set. The limit from below is set minus 1. So here we have a discontinuity. And if you want to have a look at the graph of that function, let's briefly sketch that. So let's say we have this axis here. So here's 1, 2, 3, and so on, minus 1, minus 2, and so on. And now the function, Well, if we start at 0, 0 rounded down is equal to 0, of course. And then the function is constant up to 1. At 1, the function jumps up to 1. And it's constant in between, so it looks like this, right? Then the next interval, it's again constant up to 2. And at 2, it takes a jump again, and then to 3, where it takes a jump once again, jumps up to 3 here, and so on. And of course, it's the same thing with the negative numbers, right? If you go to the left here, so anything below 0 but above -1 will be rounded down to -1, including -1 itself. So we get this behavior here. Right here it jumps at 0. And then it jumps down again. So there we get -2. Anything up to here is -2. And then here at -1, it jumps. So that is a function that is right continuous. Yeah? Meaning if you approach a point from the right, it behaves in the way you expect from the neighborhood. The function value is equal to the limit from the right. It's right continuous, but it's not left continuous. If you approach a point from the left, like this one here, you approach this x value from the left, the function value that you'd expect is this one, but the actual function value is here. So this is a right continuous, but not left continuous function. And of course, where there is a floor function, there's also a ceiling function. So for the sake of completeness, we'll define that as well. The ceiling function that is written in this way here, right? And the symbol suggests what is going to happen. We're going to round up. So this is defined as, well, the ceiling of an argument x. Oops, sorry. Is the minimum integer such that this integer is still greater or equal to x. So we're rounding up to the nearest integer. Right? Always round up, never round down. And this function, in the same way as before, is left continuous but not continuous for any integer. So this function is left continuous on R, not right continuous on the integers. And of course, it's again continuous on the open intervals between two integers because it will be constant there. Finally, a last example that is of theoretical interest, more or less only, that shows you that there are functions that are not continuous anywhere. So the worst that could happen in most practical applications is a function that has a finite number of jumps and is continuous between those jumps. But there are functions that behave very badly in this way, that are not continuous for any point on their domain. And one of those is the so-called Dirichlet function. Dirichlet function, we'll use the symbol D for that. That's defined on the reals, and the domain, the codomain is also the reals. That function is defined as d of x equals, so we have two cases here. It takes on the values 1 or 0. It is 1 if x is a rational number, and it is 0 if x is an irrational number, so a real number that is not rational. Now, this function is nowhere continuous. So not at a single point, because the reason for that is if you take any rational number in the reals, then each neighborhood of that, as small as it can be, always contains irrational numbers. So there's always a jump right next to it. And that means you cannot determine a limit. And that, of course, means the limit and the function value will not agree. So this is the Dirichlet function as an example of a nowhere continuous function. And while this might seem exotic, in practice there are functions that jump around quite a lot on quite small scales. So while they might in theory be continuous on some intervals and just have a finite number of jumps, the number of jumps might be high, so that in practice we would have to consider these functions almost non-continuous. And of course that is a problem for many techniques that we are going to apply, especially when we're talking about differentiable functions. Because as we'll later see, when we define what differentiability is, differentiability will imply continuity. But before we talk about that, we'll first have a look at some properties that are implied by continuity. And that is going to happen in the next few videos. So I'm confident I'll see you then.